The scenario presents serious ethical and legal concerns due to the inspector's lack of due diligence. Failing to thoroughly inspect the electrical system can compromise the safety and well-being of the occupants. Converting a garage into a bedroom without proper electrical upgrades can pose fire hazards, especially if the electrical panel is located in that space. Neglecting to verify compliance with the National Electrical Code, abbreviated as NEC, may result in electrical deficiencies leading to shock, fires, or appliance damage. If the inspector's negligence leads to an accident or injury, either the homeowner or the inspector could be held liable. While a quick inspection might seem convenient initially, it can negatively affect the electrical contractor. A reputation for poor work and lack of accountability can hurt the contractor's credibility, making it harder to attract future clients. Legal consequences could arise if the inspector's negligence leads to an accident, potentially implicating the electrical contractor and resulting in legal penalties. Also, a history of inadequate inspections can raise the contractor's insurance premiums. In situations like this, there are steps to take. Firstly, document the lack of inspection. Keep detailed notes and photographs of the inspector's negligent behavior. Secondly, contact the licensing authority. Report the inspector's actions to the relevant licensing authority, such as the State Electrical Board or Building Department. Thirdly, inform the homeowner. Explain the inspector's negligence to the homeowner and offer to conduct a proper inspection. Finally, protect your reputation. Keep a record of your efforts to ensure a thorough inspection and protect your reputation as a responsible electrical contractor. Although accepting a quick final inspection might be tempting, the long-term consequences of inadequate inspections can be severe. Ethical electrical contractors should prioritize safety and compliance and demand rigorous inspections to ensure the well-being of their clients and maintain professional integrity. The National Electrical Code, abbreviated NEC, is a comprehensive set of standards for electrical wiring and equipment installation in the United States. Its purpose is to safeguard people and property from electrical hazards. Compliance with the NEC is crucial for ensuring the safety and reliability of electrical systems. Several key areas are covered by NEC regulations. Firstly, grounding and bonding, which establishes the methods for grounding electrical systems to minimize the risk of electrical shock and fire. Secondly, overcurrent protection, which covers the use of circuit breakers and fuses to protect against overloads and short circuits. Thirdly, wiring methods, which specifies acceptable wiring types, installation techniques, and conduit requirements. Fourthly, equipment installation, which provides guidelines for installing various types of electrical equipment, such as panels, receptacles, and lighting fixtures. Fifthly, special occupancies, which addresses unique electrical requirements for locations such as hazardous locations, healthcare facilities, and swimming pools. Some examples of potential NEC violations in a residential setting are firstly, improper grounding. This includes failing to properly ground electrical boxes, equipment, and appliances, which can increase the risk of electrical shock. Secondly, overloaded circuits. This means connecting too many devices to a single circuit, which can cause the circuit breaker to trip or create a fire hazard. Thirdly, incorrect wiring methods. This includes using the wrong type of wire for a particular application, improperly splicing wires, or failing to protect wires from physical damage. Fourthly, missing or improperly installed ground fault circuit interrupters, also abbreviated as GFCIs. This involves not installing GFCIs in areas where they are required, such as bathrooms and kitchens, or failing to install them correctly, increasing the risk of electrical shock. Fifthly, inadequate overcurrent protection, which means using the wrong size circuit breaker or fuse for a circuit, which can allow excessive current to flow and cause a fire. The implications of NEC violations are numerous. Firstly, safety hazards, which includes increased risk of electrical shock, fire, and equipment damage. Secondly, legal and financial repercussions, which includes fines, lawsuits, and increased insurance premiums. Thirdly, difficulty selling the property, which includes potential buyers being hesitant to purchase a home with known electrical code violations. Fourthly, voiding of insurance coverage, which includes insurance companies refusing to cover damages caused by electrical fires or other incidents if the electrical system does not meet code requirements. Electrical contractors play a critical role in upholding the NEC. Firstly, they must have knowledge and training, which includes staying up to date on the latest NEC requirements and best practices. Secondly, they need to have proper installation techniques, which includes following NEC guidelines for all electrical work, including wiring, grounding, and equipment installation. Thirdly, they need to perform thorough inspections, which includes inspecting their own work and the work of others to ensure compliance with the NEC. Fourthly, they need to provide documentation, which includes providing homeowners with documentation of all electrical work performed, including permits, inspection reports, and wiring diagrams. To avoid NEC violations, contractors should follow several steps. Firstly, obtain necessary permits. This means obtaining all required electrical permits before starting any work. Secondly, conduct a thorough assessment. This involves assessing the existing electrical system and identifying any potential code violations. Thirdly, develop a detailed plan. This involves developing a detailed plan that outlines the scope of work, materials to be used, and installation methods to ensure compliance with the NEC. Fourthly, use qualified personnel. This involves using licensed and experienced electricians who are familiar with the NEC requirements. Fifthly, perform regular inspections. This includes performing regular inspections throughout the project to identify and correct any potential code violations. Sixthly, document all work. This involves documenting all electrical work performed, including wiring diagrams, test results, and inspection reports. Grounding is a critical aspect of electrical safety, serving to protect individuals from electrical shock and to prevent damage to electrical equipment. It involves creating a low-resistance path for electrical current to flow back to the source in the event of a fault. This low-resistance path facilitates the rapid tripping of overcurrent protection devices, such as circuit breakers or fuses, which interrupt the flow of electricity and minimizes the risk of harm. There are several key components of a grounding system. Firstly, the grounding electrode, which is a conductive rod, plate, or wire buried in the earth. It provides a direct connection to the earth, allowing fault current to dissipate safely. Secondly, the grounding electrode conductor, which is a wire that connects the grounding electrode to the electrical system's neutral point, typically at the service entrance. It carries fault current from the system to the grounding electrode. Thirdly, the equipment grounding conductor, which is a wire that connects the non-current carrying metal parts of electrical equipment, such as enclosures and appliances, to the grounding system. It provides a low-resistance path for fault current to flow back to the source, tripping the overcurrent protection device. Fourthly, the bonding jumper, which is a wire or strap that connects different metal parts of the electrical system together, ensuring that they are all at the same electrical potential. This minimizes the risk of electrical shock if someone comes into contact with two different metal parts. Proper grounding offers several benefits. Firstly, it provides shock protection, which reduces the risk of electrical shock by providing a low-resistance path for fault current to flow back to the source. Secondly, it offers equipment protection, which protects electrical equipment from damage by diverting fault current away from sensitive components. Thirdly, it stabilizes voltage, which helps stabilize voltage levels in the electrical system, preventing voltage fluctuations that can damage equipment. Fourthly, it reduces electrical noise, which reduces electrical noise in the system, improving the performance of sensitive electronic devices. Common grounding mistakes to avoid are firstly, improper grounding electrode installation. This includes failing to install the grounding electrode deep enough in the earth or using an improper grounding electrode material, which can compromise the effectiveness of the grounding system. Secondly, loose or corroded connections. This means failing to properly tighten grounding connections or allowing them to corrode over time, which can increase resistance and reduce the effectiveness of the grounding system. Thirdly, incorrect wiring of grounding conductors. This includes connecting grounding conductors to the wrong terminals or using the wrong size wire for grounding conductors, which can compromise the safety of the system. Fourthly, failure to bond metal parts. This means failing to bond all metal parts of the electrical system together, which can create a potential difference between different metal parts and increase the risk of electrical shock. Here are some examples of grounding requirements in specific applications. Firstly, in residential wiring, all electrical outlets, appliances, and metal enclosures must be properly grounded to protect against electrical shock. Secondly, in commercial buildings, grounding systems must be designed to handle higher fault currents and protect sensitive electronic equipment. Thirdly, in industrial facilities, grounding systems must be designed to protect against hazardous voltages and prevent explosions in hazardous locations. Regular inspection and maintenance of grounding systems are essential to ensure their continued effectiveness. Firstly, visual inspections are necessary. This involves inspecting grounding electrodes, conductors, and connections for signs of damage, corrosion, or loose connections. Secondly, continuity testing is necessary. This involves using a multimeter to verify that grounding conductors are properly connected and that there is a low resistance path to ground. Thirdly, ground resistance testing is necessary. This involves using a ground resistance tester to measure the resistance of the grounding electrode to ensure that it is within acceptable limits. Overcurrent protection is another crucial aspect of electrical safety, designed to protect electrical circuits and equipment from damage caused by excessive current flow. It involves the use of devices such as circuit breakers and fuses, which automatically interrupt the flow of electricity when the current exceeds a safe level. There are several key components of overcurrent protection. Firstly, circuit breakers, which are reusable devices that trip and interrupt the flow of electricity when the current exceeds a predetermined level. They can be manually reset after the fault has been cleared. Secondly, fuses, which are one-time use devices that melt and interrupt the flow of electricity when the current exceeds a predetermined level. They must be replaced after they have blown. Thirdly, overload relays, which are used to protect motors and other equipment from overload conditions. They sense the current flowing through the motor and trip if the current exceeds a safe level for a prolonged period. Fourthly, short-circuit protection, which is designed to quickly interrupt the flow of electricity in the event of a short circuit, which is a low-resistance path between two conductors that causes a large current to flow. Proper overcurrent protection provides several benefits. Firstly, it prevents fires, which reduces the risk of electrical fires by interrupting the flow of electricity before it can overheat wires and insulation. Secondly, it protects equipment, which protects electrical equipment from damage caused by excessive current flow. Thirdly, it minimizes downtime, which minimizes downtime by quickly interrupting the flow of electricity in the event of a fault, allowing the system to be restored quickly. Fourthly, it ensures safety, which ensures the safety of people by preventing electrical shock and other hazards. Common overcurrent protection mistakes to avoid are firstly, using the wrong size circuit breaker or fuse. This involves using a circuit breaker or fuse that is too large for the circuit, which can allow excessive current to flow and cause a fire. Secondly, bypassing overcurrent protection devices. This means bypassing circuit breakers or fuses, which can create a dangerous situation and increase the risk of electrical shock and fire. Thirdly, failing to replace blown fuses. This means failing to replace blown fuses, which can leave the circuit unprotected and increase the risk of electrical damage. Fourthly, improper installation of overcurrent protection devices. This includes failing to properly install circuit breakers or fuses, which can compromise their effectiveness and increase the risk of electrical hazards. Here are some examples of overcurrent protection requirements in specific applications. Firstly, in residential wiring, each circuit must be protected by a circuit breaker or fuse that is sized appropriately for the load. Secondly, in commercial buildings, overcurrent protection systems must be designed to handle higher fault currents and protect sensitive electronic equipment. Thirdly, in industrial facilities, overcurrent protection systems must be designed to protect against hazardous voltages and prevent explosions in hazardous locations. Regular testing and maintenance of overcurrent protection devices are essential to ensure their continued effectiveness. Firstly, visual inspections are necessary. This involves inspecting circuit breakers and fuses for signs of damage, overheating, or corrosion. Secondly, trip testing is necessary. This involves using a test device to verify that circuit breakers trip at the correct current level. Thirdly, fuse testing is necessary. This involves using a multimeter to verify that fuses are intact and that they will blow at the correct current level. Wiring methods encompass the techniques and materials used to safely and effectively install electrical wiring in buildings and other structures. Selecting the appropriate wiring method is crucial for ensuring the safety, reliability, and longevity of electrical systems. There are several common wiring methods. Firstly, non-metallic sheath cable, also known as an M cable or Romex, which consists of two or more insulated conductors enclosed in a non-metallic sheath. It is commonly used for residential wiring. Secondly, metallic conduit, which is a rigid or flexible metal tube used to protect electrical wiring. It is commonly used in commercial and industrial applications. Thirdly, electrical metallic tubing, also known as EMT, which is a thin-walled steel conduit that is easy to bend and install. It is commonly used in commercial and industrial applications. Fourthly, flexible metal conduit, also known as FMC, which is a flexible metal tube used to protect electrical wiring in locations where flexibility is required. Fifthly, armored cable, also known as AC cable or BX cable, which consists of insulated conductors wrapped in a flexible metal armor. It is commonly used in older homes and in some commercial applications. Several factors influence the selection of a wiring method. Firstly, the application. This involves considering the type of building, the environment, and the specific electrical requirements of the application. Secondly, the code requirements. This involves complying with all applicable electrical codes and standards, such as the NEC. Thirdly, the cost. This involves balancing the cost of the wiring method with its performance and durability. Fourthly, the ease of installation. This involves considering the ease of installation of the wiring method, especially for large or complex projects. Proper wiring practices are essential for electrical safety. Firstly, use the correct size wire. This involves using the correct size wire for the circuit load to prevent overheating and fire hazards. Secondly, make secure connections. This involves making secure connections to prevent loose connections, which can cause arcing and overheating. Thirdly, protect wires from damage. This involves protecting wires from physical damage, such as abrasion, impact, and exposure to moisture. Fourthly, follow code requirements. This involves following all applicable electrical codes and standards, such as the NEC. Common wiring mistakes to avoid are firstly, using the wrong type of wire. This involves using the wrong type of wire for the application, which can create a safety hazard. Secondly, overfilling conduits. This means overfilling conduits, which can make it difficult to pull wires and can cause overheating. Thirdly, damaging wires during installation. This involves damaging wires during installation, which can compromise their insulation and create a safety hazard. Fourthly, neglecting to properly support wires. This involves neglecting to properly support wires, which can cause them to sag and become damaged. Here are some examples of wiring requirements in specific applications. Firstly, in residential wiring, an M cable is commonly used for branch circuits, but metallic conduit is required in some locations, such as basements and garages. Secondly, in commercial buildings, metallic conduit is typically used for all wiring to provide protection against physical damage and fire. Thirdly, in industrial facilities, specialized wiring methods may be required to protect against hazardous chemicals, extreme temperatures, and other harsh conditions. Regular inspection and maintenance of wiring systems are essential to ensure their continued safety and reliability. Firstly, visual inspections are necessary. This involves inspecting wires, conduits, and connections for signs of damage, overheating, or corrosion. Secondly, insulation testing is necessary. This involves using a megometer to test the insulation resistance of wires to ensure that they are not damaged. Thirdly, connection testing is necessary. This involves testing connections to ensure that they are tight and secure. Ground fault circuit interrupters, also known as GFCIs, are life-saving devices that protect people from electrical shock. They work by monitoring the current flowing through a circuit and quickly interrupting the flow of electricity if a ground fault is detected. A ground fault occurs when electricity flows through an unintended path to ground, such as through a person's body. GFCIs are designed to trip quickly, typically within milliseconds, to prevent serious injury or death. There are several types of GFCIs. Firstly, receptacle GFCIs, which are installed in place of standard electrical outlets and provide GFCI protection for devices plugged into them. Secondly, circuit breaker GFCIs, which are installed in the electrical panel and provide GFCI protection for an entire circuit. Thirdly, portable GFCIs, which are portable devices that can be plugged into standard electrical outlets to provide GFCI protection for temporary applications. GFCIs work by comparing the current flowing through the hot and neutral wires in a circuit. If there is a difference of more than a few milliamperes, it indicates that some of the current is leaking to ground, which could be through a person's body. When a ground fault is detected, the GFCI quickly trips, interrupting the flow of electricity and preventing serious injury. GFCIs offer several benefits. Firstly, they prevent electrical shock, which reduces the risk of electrical shock by quickly interrupting the flow of electricity in the event of a ground fault. Secondly, they protect against electrocution, which prevents electrocution by quickly interrupting the flow of electricity before it can cause serious injury or death. Thirdly, they reduce the risk of electrical fires, which reduces the risk of electrical fires by preventing ground faults from causing overheating and arcing. Fourthly, they improve safety, which improves safety in homes, workplaces, and other environments. GFCIs are required in several locations. Firstly, in bathrooms, where water is present, increasing the risk of electrical shock. Secondly, in kitchens, where water and appliances are present, increasing the risk of electrical shock. Thirdly, in garages, where tools and equipment are used, increasing the risk of electrical shock. Fourthly, outdoors, where exposure to moisture increases the risk of electrical shock. Testing GFCIs regularly is essential to ensure that they are functioning properly. GFCIs should be tested at least once a month by pressing the test button on the device. If the GFCI trips, it is working properly. If the GFCI does not trip, it should be replaced immediately. Common GFCI mistakes to avoid are: firstly, failing to install GFCIs in required locations, which can leave people vulnerable to electrical shock. Secondly, improper wiring of GFCIs, which can prevent them from functioning properly. Thirdly, failing to test GFCIs regularly, which can result in a false sense of security. Fourthly, using GFCIs to protect against overloads or short circuits, which is not their intended purpose. Here are some examples of GFCI requirements in specific applications. Firstly, in residential wiring, GFCIs are required in bathrooms, kitchens, garages, and outdoors. Secondly, in commercial buildings, GFCIs are required in restrooms, break rooms, and other areas where water is present. Thirdly, in industrial facilities, GFCIs may be required in areas where workers are exposed to wet or damp conditions. Electrical panels are essential components of electrical systems, serving as the central distribution point for electricity throughout a building. They house circuit breakers or fuses that protect individual circuits from overloads and short circuits. Understanding the function, components, and safety considerations of electrical panels is crucial for ensuring the safe and reliable operation of electrical systems. There are several key components of electrical panels. Firstly, the main breaker, which is the primary overcurrent protection device for the entire electrical panel. It disconnects all power to the panel in the event of a major fault. Secondly, circuit breakers, which are reusable overcurrent protection devices that trip and interrupt the flow of electricity when the current exceeds a predetermined level. Thirdly, bus bars, which are conductive bars that distribute electricity from the main breaker to the individual circuit breakers. Fourthly, neutral bar, which is a conductive bar that provides a return path for current in the electrical system. Fifthly, ground bar, which is a conductive bar that is connected to the grounding system and provides a path for fault current to flow back to the source. Electrical panels function by receiving electricity from the utility company and distributing it to individual circuits throughout the building. The main breaker protects the entire panel from overloads and short circuits. Circuit breakers protect individual circuits from overloads and short circuits. When an overcurrent condition occurs, the circuit breaker trips, interrupting the flow of electricity and preventing damage to the circuit and equipment. Proper electrical panel installation and maintenance are essential for safety. Firstly, install the panel in a dry, accessible location. This involves installing the panel in a dry location that is easily accessible for inspection and maintenance. Secondly, ensure proper grounding. This involves ensuring that the panel is properly grounded to protect against electrical shock. Thirdly, label all circuits clearly. This involves labeling all circuits clearly to identify the devices and equipment that they serve. Fourthly, keep the panel clean and free of obstructions. This involves keeping the panel clean and free of obstructions to allow for proper ventilation and prevent overheating. Common electrical panel safety hazards to avoid are firstly, overloaded circuits, which can cause overheating and fire hazards. Secondly, loose connections, which can cause arcing and overheating. Thirdly, damaged circuit breakers, which can fail to trip in the event of an overcurrent condition. Fourthly, improper wiring, which can create a safety hazard. Here are some examples of electrical panel requirements in specific applications. Firstly, in residential wiring, electrical panels must be sized appropriately for the load and must meet all applicable code requirements. Secondly, in commercial buildings, electrical panels must be designed to handle higher loads and must meet more stringent code requirements. Thirdly, in industrial facilities, electrical panels must be designed to withstand harsh environments and must meet specialized safety requirements. Regular inspection and maintenance of electrical panels are essential to ensure their continued safety and reliability. Firstly, visual inspections are necessary. This involves inspecting the panel for signs of damage, overheating, or corrosion. Secondly, circuit breaker testing is necessary. This involves testing circuit breakers to ensure that they trip at the correct current level. Thirdly, connection testing is necessary. This involves testing connections to ensure that they are tight and secure. Electrical inspections are essential for ensuring the safety and compliance of electrical installations. They are typically performed by qualified electrical inspectors who are trained to identify potential hazards and code violations. Understanding the purpose, scope, and process of electrical inspections is crucial for homeowners, contractors, and building owners. The purpose of electrical inspections is to ensure that electrical installations meet all applicable codes and standards, such as the NEC. Secondly, to identify potential safety hazards, such as overloaded circuits, loose connections, and damaged wiring. Thirdly, to protect people and property from electrical shock, fire, and other hazards. The scope of electrical inspections varies depending on the type of installation and the jurisdiction. However, electrical inspections typically cover the following areas. Firstly, wiring methods, including the type, size, and installation of conductors. Secondly, grounding and bonding, including the proper installation of grounding electrodes and bonding jumpers. Thirdly, overcurrent protection, including the correct sizing and installation of circuit breakers and fuses. Fourthly, equipment installation, including the proper installation of electrical panels, outlets, and lighting fixtures. The electrical inspection process typically involves the following steps. Firstly, scheduling the inspection. This involves contacting the local building department or a qualified electrical inspector to schedule the inspection. Secondly, preparing for the inspection. This involves ensuring that the electrical installation is complete and accessible for inspection. Thirdly, the inspection. This involves the inspector reviewing the electrical installation for compliance with codes and standards. Fourthly, the inspection report. This involves the inspector providing a written report that identifies any code violations or safety hazards. Common electrical inspection failures to avoid are firstly, improper wiring methods. This includes using the wrong type of wire for the application, improperly splicing wires, or failing to protect wires from physical damage. Secondly, inadequate grounding and bonding. This involves failing to properly ground electrical boxes, equipment, and appliances, or failing to bond metal parts together. Thirdly, insufficient overcurrent protection. This includes using the wrong size circuit breaker or fuse for a circuit, or bypassing overcurrent protection devices. Fourthly, incorrect equipment installation. This involves failing to properly install electrical panels, outlets, and lighting fixtures, or using equipment that is not listed or labeled. Here are some tips for preparing for an electrical inspection. Firstly, obtain necessary permits. This involves obtaining all required electrical permits before starting any work. Secondly, follow code requirements. This involves following all applicable electrical codes and standards, such as the NEC. Thirdly, use qualified personnel. This involves using licensed and experienced electricians who are familiar with the code requirements. Fourthly, document all work. This involves documenting all electrical work performed, including wiring diagrams, test results, and inspection reports. The consequences of failing an electrical inspection can vary depending on the jurisdiction. However, they typically include the following. Firstly, required repairs. This involves requiring the homeowner or contractor to correct any code violations or safety hazards. Secondly, fines. This involves imposing fines for code violations. Thirdly, delays. This involves delaying the completion of the project until all code violations have been corrected. Fourthly, legal action. This involves taking legal action against the homeowner or contractor. In summary, understanding electrical principles, safety practices, and code requirements is crucial for ensuring the safety and reliability of electrical systems. This knowledge empowers individuals to make informed decisions, avoid potential hazards, and maintain a safe electrical environment.